All right, let's begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Thank you again, Lord, for these students. I just pray that you'd help us to use this time wisely just to wrap up our thinking on chapter 12. And again, Lord, we thank you for your many blessings to us this day, Lord. In your name I pray. Amen. So, maybe you have any questions about section 12.9 in particular? Probably we should focus there if you got questions.
32.
Yeah. Number 32. Let me put a 32 tilde. How about this? Integral from 0 to 1 of cosine of x squared dx equals blank within, what was it, 0.01? Okay, so basically the idea here is to replace the integrand with a power series, integrate term by term. This will give us, after application of the fundamental theorem of calculus, it'll give us an alternating numerical series, which we can calculate to arbitrary order using the alternating series estimation theorem. So like, here's how that goes. This is the integral of what? 1. So we use the cosine of u, right? Is 1 minus 1/2 u squared plus 1 over 24 u to the 4th and so forth. Minus the nth term is what? Minus 1 to the n over 2n factorial u to the 2n, right? So if you plug in u equals to x squared, right? Set u equals to x squared, then what do we have? We got like 1 minus 1/2, let's see here, x to the 4th, yeah? Let's see here, what's x squared to the 4th power? Eighth and so forth, right? So let me just say the integral of cosine of x squared. Let's just work out an antiderivative to start with, all right? Now that's what? That's going to be x minus 1 over what? 10, x to the 5th, plus 1 over 9 times 24, x to the 9th, plus dot, 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 dot. I mean, what's like an arbitrary term? It would be x to the what? Minus 1 to the n over what? Over 2n factorial times what? Times 2n plus 1, x to the what? See, x squared to the 2n is what? It's x to the 4n, right? So 4n plus 1. Oh, sorry, I should do what? Oopsie daisies. Let's see here. This is supposed to be what? 4n plus 1, right, when I integrate? And then so forth, right? I mean, plus it's an infinite series is the antiderivative. So this is an antiderivative of the given integrand, right? So then, of cosine of x squared, I can integrate from 0 to 1 of cosine of x squared. And what do I get? Well, what happens when you plug 0 into the series? Well, yeah, let me call this whole stupid thing f of x, all right? So this would be what? This is f of 1 minus f of 0, right? F of 0 is just straight up 0, as you guys just told me. And so we have what? You just plug in 1, right? I've got 1 minus 1/10 plus 1 over 9 times 24 plus dot, 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 dot. Eventually we get to the what? Minus 1 to the n over 2n factorial 4n plus 1, yeah. Now I may not even need that nth term. What am I supposed to, I'm supposed to do what? I'm supposed to find the error, right? So let's just stop here and just categorize, like just me tabulate a couple of results. Here's how I think about it. So like, for example, one of the things I can immediately see is the integral from 0 to 1 of cosine of x squared dx is equal to 1. And that has an error of at most what? Error at most what? The next thing I haven't used, right? 1/10. So this is the alternating series estimation theorem that says that the error is at most the next thing you haven't used. All right. What if I do the integral 0 to 1 cosine of x squared? What will be the next approximation? 9/10, right? How close is that to the truth? Alternating series estimation theorem says it's the next thing you didn't use, which is this. Right? If I do the integral from 0 to 1 of cosine of x squared dx is equal to 1 minus 1/10 plus plus minus 1 to the n minus 1 over 2 times n minus 1 factorial times 4 times n minus 1 plus 1, then this has an error of what? At most 1 over 2n factorial times 4n plus 1. That might be important to know if I was asked to find this integral to within some like larger, I mean like really small precision. Now the question is just 0.1 though, right? So you can just plug this number in your calculator. Like what's 1 over 9 times 24? Is it smaller than 0.1? 0.01? I think so, right? That's 216. That is actually about 0.0046, right? That's less than 0.01. So there you go. This integral is 0.9 to within, certainly to within a tolerance of 0.01. Now your homework problem isn't exactly this, right? What's the difference with the homework problem? It's sine of x squared, but same logic, right? Does that make sense?
So you don't need to use Lagrange's.
Oh, there's no need. No need for Lagrange's estimation theory here. I mean, because this is an alternating series, so. And just generically speaking, that's a good rule of thumb if you're using, it'll get you pretty far without getting into too much trouble. Generally speaking, if you take the next term you're not using, that's probably a good bound on your error. People, there have to be some series out there that dance around a little bit as they're, and like in the second section I came to one where that the size of the terms was kind of playing games. Like, I actually had a term that was in a higher order that had a larger coefficient, one on a lower order that had smaller coefficient. We see this all the time with series that just have like even terms and then like no odd terms or something. Of course, the odd terms will be 0, right? So that's smaller than the even terms. You don't even really think about it. But there can be more malevolent things. But certainly for an alternating series, just use the alternating series estimation theorem. That's the easy way. Other questions? One of the things I wanted to show you was just an example. This is relevant to some of your homework. If I have something like f of x equals to the natural log of, 7 plus 6x, let's say. And I want to find the Maclaurin expansion, right? If I'm going to do that directly, I got a couple different options. So here's the way that, I kind of come back to. df dx is 6 over 7 plus 6x, right? And then, okay, well that's not quite what I want, because I want a 1 here, right? How do you make a 1 there? Well, factor out the 7, right? And then I'm like, yay. So that is the sum, k equals 0 to infinity, 6 over 7, minus 1 to the k, 6x over 7 to the k power by the geometric series, right? We have a equals to 6/7, and the ratio is 6x over 7, right? Minus, rather, because I need a minus, right? And then you can clean this up, right? Let's clean it up. What is it? It's important to clean it up before you try to integrate. One of the big mistakes I see people make on the test when they haven't studied enough is they haven't picked up on the fact that they need to simplify this expression before they integrate. If you don't, well, I don't know. You may or may not get it right, depending on if you calculate correctly in the next step. But odds are kind of against you calculating correctly in the step after this if you don't do this one right. Let's see here, x to the k, like that. So what did I do? I just collected all the 6s and 7s together, and all right. I guess technically the step before, maybe I should put the minus inside to show you the logic if you want. I mean, we could do that, but I'm going to leave it. Now I integrate. This is for what? The absolute value of r equal to the absolute value of minus 6x over 7, less than 1. So what's the interval of convergence here? Oh, I guess 7/6 to minus 7/6, right? The endpoints are not included because this is geometric, right? Then what? Integrate. What do we get? F of x is equal to, well, a constant, right? But you kind of already know that's going to be 0 for this example. Now, what is this like? This problem I'm doing is an awful lot like one of your homework problems, right? Which one is it? Number 6, yeah. Let's see here, f of 0 is what? Oh, it's natural log of 7. I think in my office earlier today, I think I talked us out of I had worked too hard to make the example. So, oh look, f of 0 is natural log of 7 here, but that's also equal to what? C plus the 0 series, right? So, there you go. Natural log of 7 plus 6x is equal to this lovely series, k equals 0 to infinity. Minus 1 to the k, I'll put that first. And I'll write 6 over 7 because, I don't know, it just seems right. 6 over 7 k to the k plus 1 power times 1 over k plus 1 times x to the k plus 1. There you go. Thank you. I think I was talking to Thomas earlier today, and he had an interesting and useful other idea about how you could do this. Do you guys have any other ideas about how you could do this? Yes, Will?
You can go ahead and, in the beginning, separate your terms in the natural log. So you factor out a 7 of that. You get natural log of 7 times 1 plus 6 over 7x. And then you can use logarithmic rules and stuff like that.
So you're like this, and then that's the natural log of 7 plus the natural log of 1 plus 6x over 7. Now, if you really want to be lazy, you should say, I'm going to say that's the natural log of 7, and I like people being lazy in this sense, 1 plus u. We already worked this out the other day, right? That's the sum, k equals 0 to infinity, minus 1 to the k over k plus 1, u to the k plus 1, right? So this is the natural log of 7 plus the sum k equals 0 to infinity minus 1 to the k over k plus 1 times, yeah, 6x over 7 to the power k. I seem to have lost a, k plus 1, yeah. So then one more step, then you'll get back to here, right? Because 6x over 7 to the k plus 1 is what? It's 6/7 to the k plus 1 times x to the k plus 1, right? So these are the same answer. I mean, that's definitely a nice way of working this problem, right? But when I think about it as a method for solving a test problem, there is one thing that you have to have here in order to make it work, which is what? You have to know the power series of the natural log of 1 plus u from memory. Or you have to be able to derive that one. Now, if you guys want to memorize the power series expansion for natural log of 1 plus u, that's fine with me. But it's not fine with me if I have a question on the test where the problem says, you know, find or derive, let's say, Maclaurin series for f of x equal to the natural log of 1 plus x. I mean, if I ask you that question and you just tell me the answer, I'm not going to be that happy about it. Right? I want you to derive it if I say that. In other words, you have to show it from more basic facts, either geometric series arguments or the other thing, what? Direct differentiation, Taylor series. You could do it that way too. Unless, of course, the instructions might read derive using geometric series techniques, you know, the Maclaurin series expansion for that, in which case I'd actually want you to go through the steps which are analogous to this one. Yeah. Will, you asked me about 1 minus x cubed. Was it 1 minus x cubed? Let's talk about that one. So you guys know the, I guess I'll work over here. Have you guys ever seen this? I mean, I think I've done it before near, right? And so forth, right? This is what? Yes, Pascal's triangle. And so it tells us things like a plus b, quantity squared, is what? Right? Oh, before that, I guess it tells us that a plus b to the 1 is what? Yeah, and before that, there's a plus b to the 0 is what? Yeah, a plus b to the 0 is just, 1. But then, you know, it does start getting more exciting when you get here. Or you get here. Etc., you know. But the point is, this Pascal's triangle. What I'm writing right here, you can write sort of more, let's say, generically, a plus b to the n power. It's equal to the sum, right? K equals 0 to n of what? N choose k, a to the power, how's it go? N minus k, b to the power k, right? And these binomial coefficients, right? These you can also find where? These are the numbers in Pascal's triangle, right? Like this, for example, is what? This is 5 choose 1, 5 choose 2. This one is 5 choose 3, 5 choose 4, This is 5 choose what? 5. How many ways are there to choose 0 from 5? There's one way. Binomial coefficients. Now, great. So as long as n is an integer, right? This makes sense, right? Or even 0. We could say it extends to the top of the triangle. But what if it's not an integer? What if it's not a positive integer, right? So what about something like 1 plus x to the alpha power? And this alpha doesn't have to be a whole number. Well, then you can say that this is equal to f of x, right? And then you have like what? F of 0 is what? 1, right? What's f prime of x? Usually you put a k up here, actually. Right? So f prime of 0 is k, right? What's f prime prime? Right? See where we're going? What's the nth derivative? It would be k times k minus 1 times k minus 2, and so forth and so on until we get to what? K minus what? K minus n? Not quite right, right? If n equals 2, we go to 1. So it's k minus n minus 1, right? So if you divide this by n factorial, which would give us the coefficient in the Taylor expansion, right? Then we get this from Taylor's theorem, basically the following. 1 plus x to the power k is equal to a sum, right? Say n equals 0 to infinity. I shouldn't use k because I shouldn't use k for the sum. K is a fixed thing over here in this case, right? And then the coefficients look like this, right? K times k minus 1, k minus n minus 1, divided by n factorial, x to the power n. In the case that k is a positive integer, what happens to this calculation? This is just a polynomial, right? After you differentiate more than k times, what happens? This is a kth order polynomial, right? If you differentiate k plus 1 times, you get 0. K plus 2 times, 0, 0, 0, 0, right? This infinite series truncates, right? At what? At order k, right? In fact, this infinite series goes back to this animal up here, right? If I put 1 x k n equals 0 to k. Oh, unfortunate. Sorry, guys. I just realized the badness. Oh, man. K minus. Oh, man. What an unfortunate nomenclature here. There, I fixed it now. And then this C here. Oh, that wouldn't be very exciting, wouldn't it? What's 1 to the k minus n is what? Yeah, that doesn't really show up, does it? So. But on the other hand, you also learn that these binomial coefficients also have a formula, right? Which is k over n is equal to what? This thing, right? I mean, we can try it out. Does it work? Let's check it. What if we look at like 5 choose 3? What should that be? If we believe Taylor's theorem, it should be what? 5 times 4. I go all the way to 5 times 4 times what? 5 minus, not 3, but 2, right? So I get all the way to 3, right? Because 5 minus 2 is 3. That's where this stops. And I divide by what? N factorial, which in this case is 3. Which does give me? Which is otherwise known as 10. Well, what do you know? Okay, so that's why we have this formula for the binomial coefficient, because of this connection with Taylor's theorem. Right? Now, Will, you asked me about 1 plus x to the minus 3 power. I think it was, wasn't it?
Yes.
Now, it didn't look like that to the start. It looked like 1 over 1 plus x cubed, was it?
Yes.
All right. So like this one, I can find the complete series by using a geometric series technique, right? But if I just want the first few terms, I see this as a binomial series. This, folks, right here, where am I? Let me box it in. This is the binomial series. And if I write out the, oh man, I forgot to write out the first few terms. So like 1, I should probably write them over here. So this is 1 plus x to the what? To the minus 3, right? So this is binomial series, right? K equals to minus 3. And if you, let me just write it symbolically for a second here. This is 1 plus kx plus 1/2 k times k minus 1 x squared plus 1 over 3 factorial k times k minus 1 times k minus 2 x cubed. And so what is that? Well, that's 1 minus 3x plus 1/2 of what? Minus 3 times minus 4x squared plus 1 over 3 factorial minus 3 times minus 4 times minus 5 x cubed. And see, I could keep going. You see how the pattern goes? You do 1 over n factorial, and then k minus 1, k minus 2, all the way up until 1 less than the power you're at. This is the binomial series. It's a pretty simple pattern to learn, right? And there it is. So like this is what? Let's see, that's what? That's a 6. This is a 12. That gives me 2. Looks like minus 10. That was the answer in the back. This was an odd problem, right?
Even.
Oh, it was even? Oh, man. Sorry. I seem to have done your homework for you.
Well, that's why it's a 1 minus x.
Oh, 1 minus x cubed. Well, that does change things a little bit, right? But not that much. Because you could easily, like, I mean, we think of all of these. I mean, to get the most mileage out of our thinking, you always want to think about substitutions, right? So I did this with x because that's what we're comfortable with, right? But in fact, how do I want to use it eventually? Like this, right? So how could I find the total series here without using binomial series and by direct calculation? As you can see, finding the arbitrary formula for the nth term, the nth coefficient here would be kind of a drag. Like, for example, if I asked you, what's the 73rd derivative? I guess you could still do it. I mean, this is actually a, okay, fine. I admit defeat. This is a good, like, stone cold formula for the nth coefficient, right? I mean, it is. It's not as nice as some of the other formulas we had, but it's a formula. So if I asked you to calculate the 73rd derivative or that or something, you actually have a shot at it, right? Because you just have to use like the binomial coefficient and like match powers like we did. I mean, there's hope. The other way I can think to do this, though, is through the geometric series technique, right? Like, you could look at this as what? F of x, 1 over 1 plus x cubed, right? So the integral of f of x is what? Minus 1 over what? 2, 1 plus x squared, plus a constant. And then the integral of f of x dx, the double integral, not in the sense of calculus 3, sorry. That would be 1 over 2 times 1 plus x, I believe, plus cx plus, say, c2, right? Then this is 1/2 the sum k equals 0 to infinity of minus 1 to the k, x to the power k, plus cx plus c2. And then I have to do what? Differentiate 2 times. Differentiating twice gets me to what? K equals 2 to infinity, minus 1 to the k. I've got a k times k minus 1 divided by 2, x to the k minus 2. These differentiate nothing. Yay, they're gone. Bye. And that's, yeah. If I haven't made some stupid mistake, that's also the power series for 1 plus x cubed. Does it match? Moment of truth. If I plug in, If I plug in, If I plug in k equals to 2, what do I get? 2 times 1 divided by 2. 1? 1. Well, so far so good. And then plug in k equals to 3. 3 times 2 divided by 2 gives me 3. That's a minus 3. X. And then plug in k equals 4 plus 4 over 2 is 2 times 3 is 6. All right. I believe we're good. Plus, so you see, there are 2 roads you can go down. Right. But in the end, it's still the same road that we're on, you know? Just saying. Other questions? Obviously, the advantage of the geometric series trick is that you don't have to remember the binomial series for this problem, right? I mean, the more tools you know, the safer you are, right? Number 20, you say? Expand f of x in powers of x. You've got x squared plus x times natural log of 1 plus x. So what I would do here is I would divide and conquer. And I don't literally mean divide, I really mean multiply and conquer. X squared, distribute and conquer perhaps would be better. Anyway, stupid puns aside, look at it like this, right? But these are already in our toy chest, right? So this is x squared. Sum k equals 0 to infinity. Minus 1 should be k plus 1. Sorry, this problem's not boring. I don't mean to misconstrue it. Let's see here. X times the sum. I need to get some coffee. Let's see here, minus 1 k plus 1. K plus 1. X to the k plus 1. All right, and then, right, then multiply in. And those will be, you probably can combine them then. I think about how to make a nice answer here. So that's what? That's k equals 0 to infinity, minus 1 to the k plus 1 over k plus 1 times x to the k plus what? K plus 3. And then plus the sum k equals 0 to infinity, minus 1 to the k plus 1 over k plus 1, x to the what? K plus 2. Yeah, so then I can, this is not the final answer, right? We can coalesce these into one series, right? What do you want to do? We need to make a substitution on both of them. Let's make them sort of meet in the middle. Let's say that this, we're going to set j equal to k plus 3. And over here, we're going to set j equals to k plus 2, right? To make them have the same format. Now, j equals to what here then? Looks like to me 3, 4, 5, and so forth, right? Over here, if you look at it, j starts where? 2, 3, 4, and so forth, right? So this is the odd man out. This one is weird. We should just split that off. So when I plug in the lowest order term here, what do I get? I get x squared, and this is what? 1, right? K equals 0. Oh, did I get minus 1 there?
No, it's supposed to be 1.
Oh, thank you. I was about to get really confused. So you guys see this is a mistake. I should have minus 1 to the k. Did I do that before too?
No.
Oh, so I got it right up here. But, okay, so my point is when we plug in k equals to 0, we get just x squared. All right, and then we're going to have a plus a sum, j equals to 3 to infinity of stuff, over here x to the power j. To figure out what goes in here, we just have to make the appropriate substitution, right? So this gives me k is equal to j minus 3. This gives me k is equal to j minus 2. So let's see here. I mean, we could simplify this further, but minus 1 to the j minus 3 divided by k plus 1, which is what? J minus 2, plus what? Minus 1 to the j minus 2 divided by what? K plus 1, which is what? What goes here? It was k plus 1, j minus 1. Very good. Now this we could simplify, right? This we could rewrite as minus 1 to the j, right? That there's a common thing there. And then we just have, that would be a square. So I could write that as 1 over j minus 1 minus 1 over j minus 2. That coefficient can be simplified like that. That's prettier, I think, yeah? And you could even make a common fraction if you wanted, but whatever, I'll stop there. The simplification at the end is slightly less important than the big idea here, which is that we can combine the series, right, by relabeling them as to make them, match. What's today? Thursday, isn't it? Oh, I still have so many minutes to go. Sorry, I have to regroup. 1 minute. I need I was thinking we were out of time. I'm an idiot. Does that make sense? Now, sometimes the book just wants you to write out like the first 3 terms or something, right? For this one, what would the first few terms look like? Oh, man, we'll forget this. Oh, man. That was close. I haven't hit a student yet, but that one might have required some dodging. You see, it's catching. Let's see here. Let's see here. What is actually the natural log of 1 plus x? If you just write this out, it's what? It's 1 minus what? See, because k equals 0 gives me 1. K equals 1 gives me 2 here. I think it's 1 minus 1/2 x, isn't it? Plus 1/3 x squared. Yeah. So this would be x squared plus x. 1 minus 1/2 x plus 1/3 x cubed. So if I want to find the power series for this function to third order, right? So on the test, I like to ask an amalgam of these kinds of calculations, right? Sometimes I might ask for the full series, and for other problems, I just ask for the first few terms, right? I like to test on whether you guys can multiply series by asking for the first few terms, right? Because actually multiplying full series out is usually kind of like, well, we would need more time. But you know, just the first few terms, well, that makes a nice shorter test question, right? And it's also an important skill. Let's see here. So this is, let's see here, what's the lowest term? Just x, right? Yeah. And then let's see here, I like to group things. X squared times what? I've got a 1. And then I've also got this minus 1/2, right? So I've got, for x squared, I've got x squared times 1, but also x times minus 1/2. That's it, though. For x cubed, what do I got? Yeah, minus, I mean, depending on how you want to order things, minus 1/2, right? And then this times that gives me, you say plus 1/3? Oh, I mean, that's x to the 4th, isn't it? So it's just that one? There's no other way? Yeah, because, wait, what? Hold on a second. Don't buy that. Come on, you guys. You're going to believe this? Sometimes I just feel like I'm talking to myself in here. Let's see. Let's see here. X squared times 1 is x. And I think the story up till now was not corrupted by that insidious mistake. Minus 1/2. Yeah, okay. Now we're at x cubed. So we still got the minus 1/2 term, but now we also have the plus 1/3. Yeah, I knew there was something askew. And that's all I need to get the third order, right? And so what do we get? X plus 1/2 x squared. Then what? That's weird. This is very troubling. This is most troubling. And sometimes it's good to do this because you can check your work on something else, yes? And you may find that you don't like what you see, right? Yep.
The
Oh, okay. Thank you. Compare that and this. Well, man.
I'm looking at when you solve for the power of 1 plus x, and the series expansion you got had an x multiplied by every term, the one that's on the board right now.
Oh, really?
So it was x minus x squared to x cubed over 3.
Ah, so what I was claiming was the natural. Okay, so the moral of the story here is I shouldn't assume I remember anything from memory. We should derive everything, right? So what you're telling me is when I worked out natural log 1 plus x before, I got the sum. In fact, k equals 0 to infinity, minus 1 to the k, divided by k plus 1, x to the k plus 1, which starts at x, and then goes minus 1 half x squared, and then goes 1/3 x cubed, and so forth, right? Correct? Is that right? So, yeah, because I was about to get really confused because, look, this has this x squared term here, right? There's no x, like it starts at x up here, and you see what's wrong is that, let me make the correction. Let's see here. So this was supposed to be what? X squared. Apparently that was actually right. X cubed for the wrong reasons. And everything stays the same. It just, this becomes squared, cubed, and 4th power. Right. Let me just check on it. X cubed gives me a 1, but also a minus a half. X to the 4th gives me minus a half, but also a plus a third. Yes. So this is the power series, the Maclaurin series for x squared plus x times natural log of 1 plus x to 4th order. And we can check our answer, right? We can check against this. X squareds match, right? What happens when you plug in j equals to 3? J equals to 3 gives me minus 1, right, times a half minus 1, which is minus a half times minus 1, which is a half. When you plug in j equals to 4, j equals to 4 gives me this is a half and this is a third. I get a third minus a half, which is minus a sixth. Yeah. So as you can see, they should match, right? I mean, of course. Was this one of your homework problems?
Yeah.
Oh, I'm sorry. Man. Trick me into doing your homework again. How dare you? How dare you, you monsters? All right, I'll get over it. Anyway, next question. 42. 42. We'll call this 42 tilde. Suppose you're asked to sum the following series. Sum k equals 0 to infinity, 1 over k factorial, x to the 7k plus 3. What? Who's calling me? Yes. Pretty good. I'm teaching right now. Hi, class. We were talking about Miss Deacon earlier today. We were talking about how you were used to be on Team Edward. Mm-hmm. 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 Okay, back to there. Bye. All right, there we go. So nothing pressing. I don't know, whatever. It's fine. Stephanie does not have my schedule, so it's understandable. Now, when my wife calls me in class, it's on purpose. But I also don't object anyway. See what I did? The reason I did this, and you can work the problem 42 much the same way, is it looks to me like what? When I look at this, I go, that is almost the power series for the exponential, right? So what I want to do is rewrite it so I can see it as a substitution of the exponential series. So that plus 3 is an anomaly. I need to get that off. So that's just multiplication by x cubed. But then this x to the 7, x to the 7k is also equal to x to the 7 to the k power, right, by laws of exponents. So this is the exponential of x to the 7th times x cubed. There you go. I summed the series. So looking at your problem, I think the answer would be x times e to the x cubed. But I'll let you work it out. Well, 41, okay, I look at 41, I go, that's e to the x cubed. Let's check the answer. I'm looking for some affirmation in my life. Let's see here. Oh, e to the x squared. What do you know? 41, e to the x squared. What? Poppycock. That's unadulterated nonsense. That is most certainly not e to the x squared. E to the x squared. Really? No, sir, no how. 41 has a wrong answer. That's pretty rare. I haven't found many wrong answers in the back of the book for that. I mean, I think that's my first one this semester. Do you guys remember finding a wrong answer in the back of the book up till now? I don't. Yeah, interesting. I mean, I'm pretty sure about my logic here. Now, if you look at like 43, it's almost an exponential series, but it's been like differentiated, right? So like if you integrate that series term by term, you'll get to what? The integral of that series is what? The 43 is like 3k over k factorial, x to the what? 3k minus 1. And the sum what? All right, so if this thing is f of x, then the integral of f of x is what? Term by term. Right? Which I would argue is, I think there's just a typo in the key there. I'm glad I didn't give you guys some like speech about looking at similar problems in the homework. I would feel very silly at this point because it's misleading, that e to the x squared problem. Now, if that's the integral, then f of x is what? Right? Differentiating. And if you look at number 43, I think that was the answer to 43. Yay, that is the answer to 43 at least. Anyway, this, as you can see, there are many games we could play here, yes? They're based on like using integration, term-by-term integration, differentiation, paired with the known Maclaurin series. There's a variety of malevolent and unanticipated problems that you can ask here as an instructor. I find for the most part, if I make the bulk of the test just on the stuff I've done, though, I don't really have to work that hard to confuse you guys, because this material I think is difficult, and collectively. So like the test is probably what? It's probably something like 50% convergence, divergence, 50% this calculation stuff, right? And when I say convergence, divergence, I'm including interval of convergence, all right? So and even in the convergence, divergence, there's really two cans of worms, right? There's the numerical series stuff, which I think is the hardest conceptually, personally. I mean, there's just so much there. Like we have about, 9 different tests. And then, on the other hand, the interval of convergence, here is a power series, find its interval of convergence. That's not so bad, is it? I mean, you apply the ratio test, that gets most of it, and then you got to check endpoints. Or it's geometric, so you know the interval of convergence right off the bat, just from the geometric series result. If you had to pack your bag mentally, what's the one thing you'd put in it for this test? Textbook. It's like, if you had one wish, what would you wish for? Unlimited wishes. No, that is not an allowed answer. Always one more wish than I've already made. No, same answer. No, I think the geometric series would be a good thing to take with you, yeah? I mean, geometric series, we've certainly got the most mileage out of that example. Followed closely thereafter maybe by the exponential series, but that's just a convenience. I mean, geometric series is everywhere. Well, any questions? Other questions, I should say. Tomorrow I'll be diving into chapter 10. Have no fear, that will not be on the test next Tuesday, all right? Monday, I've set aside for questions you have about this material, and so I'll collect the homework tomorrow, and then we'll be on to chapter 10. So that's pretty much all I got for you guys today, unless you have another question. Yeah.
I have a question that's not a homework question. I'm just
Sure.
curious. So, the Taylor series expansion for sine of x.
Yep.
That's -1 to whatever it is. I don't remember.
All right.
I'm curious, when you plug in k equals 0, if you get a 0 in the bottom fraction for one of them, it's either the cosine or the sine one, because it's the 2k factorial in the bottom.
Yeah, sure.
Oh, no, I lied, never mind. 0 factorial is 1, correct?
Yes, I was getting there, but yeah, that's the thing is, yes, if you, it's the cosine you're thinking of, but yeah. So yeah, the point is 0 factorial is 1. One of the many reasons we have to make it that, yeah. There is one other thing I might mention. There's one other calculation I wanted to just mention briefly is something like this f of x. If you wanted to recenter it at 1, you might do this, right? I'm taking this guy. Okay. So this, if I wanted to recenter at 1, what I would do, it would be subtract 1 and then add 1 again, which would be doing what? Plus 6 in this case, right? At which point we would have the natural log of 13